Okay. Can you guys see my Excel sheet?
Yeah.
Yep.
Okay.
Mm-hmm.
So, hold on one second. Okay. So this is basically the temperature distribution we were looking at in class, where you've got some function or some non-zero temperature at the top, and then all the other temperatures are 0. You guys, does this look familiar from your class notes?
Yeah.
Okay. So what we had said is basically if you take any circle in here, right, and any point, there's this relationship between between this point and the surrounding temperatures. If we want there to be 0 heat rate, it always has to be satisfied. That equation, that set of equations we just wrote, is satisfied. So I'm going to start here. So this is our temp distribution, which we don't know yet. So we just set it to 100. Obviously, these are not correct yet. And we're going to say the heat rate is equal to this guy plus this guy. Oh, I did that wrong. We're looking at the temperatures. So the heat rate is equal to this guy plus this guy minus 2 times this guy plus this guy plus this guy minus 2 times that guy. Okay, that's what that is just what we built up before, that last set of equations I wrote. You've got positive expressions for x plus dx and x minus dx. So that's this one and this one. You've got positive x plus or y plus dy, y minus dy, and then you've got minus 2. For each one, you've got minus 2 times the temperature evaluated at that middle point. I hope I did that correctly. Everyone feels good so far?
Mm-hmm.
Yeah. Okay. So what I'm going to do is I'm going to drag this through. Do you guys have any experience with Excel?
Yeah.
So now I've basically applied the same equation everywhere. And what you find is the one place where you've got non-zero heat rate based on this temperature distribution. Sorry, it's not non-zero heat rate, where you've got non-steady state, right? Where the sum of those things doesn't equal 0 and you're violating the steady state condition is at the top. Because when you add up all of these temperatures, there's this 100 term that isn't satisfied by the relationship between these other 3 temperatures. I guess the other 4 temperatures. Does that make sense?
Mm-hmm.
Okay. So for this to be steady state, we're interested in what the temperature distribution is going to be when you've got steady state conditions. We want to force those steady state conditions. And to do that, we have to set this energy balance everywhere to be 0. So I'm going to go to Tools, Solver, and this works on both PC and Mac. Oh no, now I have to share my solver window. One second, I'm just going to share my whole screen. Okay, you guys can see my screen?
Yeah.
No?
Yes.
Yes, okay. So, okay. So basically I want to set this guy, S5. Ooh.
Oh, no, we're joy.
I'm setting this equal to 0. I'm saying I'm going to do that by changing the variables here. I guess I've already set this up before. So I'm allowing myself to change these variables. And then it's also subject to the constraints. And basically, it's a kind of a funky way to do it, but I'm just subject to the constraints that all of these other 99 cells also equal 0. So I'm telling this thing that it can modify these cells however it likes. And all I want is this cell plus the other 99, so all 100 of these cells, to equal 0. Okay? And I'm not going to tell you what's going on under the hood. Basically, I think it's just messing around until it starts to converge. The solving method is GRG nonlinear. Okay. Hopefully my computer doesn't overheat. I've never done this while also hosting a Zoom call. Okay, so it's jumping around now. By the way, the reason this is red and blue is I've set some conditional formatting. So it's gonna look like a heat map when it's done. And hopefully this thing doesn't overheat. It should start changing the values in a minute. Hopefully I filled it in right. I think when I did it yesterday, it looked a little bit different. If this doesn't work, I have some other tabs saved that I've already. Hey!
You just did it.
Just did it. It looks, no, this is not correct yet. Right? Because there's something wrong. It's high here, it's low here, it's not symmetrical. It's way too low there. It does look nice and low here. Let's give it a minute. Oh, and now it just heated up. So now it's 33 here, 15 here. You'd expect it, where do you guys expect it to be warmest?
Probably in the center, no?
Yeah, in the center, right below the hundreds.
Yeah.
And then you expect it to be coolest in these corners. And you expect some sort of shape. Okay, now we're getting there. So now it's starting to figure out it's going to be warmer here. It still thinks it's pretty warm in these corners, which it probably won't be. It's starting to figure out that it's going to be pretty cold down here. Give it another minute. My computer's really heating up right now. So hopefully, if I just disappear,
I've actually
2,000 pieces of hardware. Okay, give it another minute. Got 53 here. So it's finally realizing that it's warmer, that the warmest points aren't the corners. Okay, and now it's heating up here, and we're starting to see this shape come together, right? It looks kind of parabolic in a way. Because this thing takes so long to run, I pre-ran a bunch of other scenarios that we can compare to. Okay, and you can see, I don't know quite how this numerical solver works, but it looks like these hotspots are slowly moving towards the center. It's slowly figuring out that the temperatures, kind of just looking at these relationships, that it needs to be hotter at the middle and cooler on the sides. So we're starting to see this band here, this white band, where it's all, around 10, 15 degrees Celsius. What is that thing called? Does anybody remember what it's called? You guys have to have your mics on so you can yell it out.
Oh,
What's it called? An isotherm, right? Isotherm just means constant temperature. So does heat flow, what's the relationship between isotherms, areas with this constant temperature, and heat flux? Does heat flow along the isotherm?
Thank you.
No.
Yeah, it flows across the isotherm. It's always perpendicular. Heat flux is always perpendicular to places where there's constant temperature.
Yeah.
One of the cool things about this is we were able to cancel out thermal conductivity. It turns out that when you don't have any internal heat generation or anything, it doesn't actually matter what thermal conductivity is. So whether this thing is made of aluminum or styrofoam, assuming you're able to enforce these boundary conditions, you get exactly the same temperature distribution, which is the same thing we saw with one-dimensional heat flow through a slab, right? When we were dealing with a slab, we knew that if we had both surfaces set at temperatures, we were just going to have a line between them. This is essentially the same math as that. We're just doing the whole thing in 2 dimensions. And it becomes a lot more complicated because you've essentially got 2 quadratics balancing each other out rather than just a linear expression. And it looks like we're basically done. That 22.7 that's red, that's just because I colored the cell before. But it's basically figured out that in this top edge here, it's going to be at its highest point, 49.1 down there. Let's see. It might actually be done. It's going to figure out it's done in a minute. And then in these bottom corners, it's constant. So this whole thing satisfies. This is what satisfies that diffusion equation. Basically, what we did is instead of going to that diffusion equation, the d squared t over dx squared plus d squared y over dy squared, we just started with the same energy balance. We wrote it in discrete terms. So we just wrote it as functions of the kind of adjacent temperatures. And then rather than trying to do some big, ugly analytical solution with hyperbolic signs, we just made Excel simultaneously solve those 100 equations. And the outcome is my computer is hanging. Which is a shame because I have all these other examples I wanted to show you. Okay. Okay, so I wanted to get to a different tab. Hopefully I still will be able to. Okay, I'm just gonna. Give me a second, guys. So basically, this is the same thing that we were just doing. I already solved it. The cool thing about this spreadsheet, and I'll send it out to you guys, is if you change any of these boundary conditions and then resolve, it will resolve all these temperatures for you. So here's an example where I made the top and the bottom both equal to 100, and then I made the sides equal to 0. And I didn't have to change anything else. I just changed these boundary conditions, and then I went back into Solver and resolved it. And it came up with this. So you've got these isotherms at 50 degrees, so exactly halfway between 0 and 100, along the central diagonal. So this is the interesting part. If we think back to the diffusion equation, what did that diffusion equation say? It's like I have a mini whiteboard. So we were able to come up with this diffusion equation, and we had it in class. And then we also derived it from the energy balance today in recitation. And we didn't really spend too much time looking at it. You guys are all still there, right?
Yeah.
So we had this thing. You guys see it? No. It got worse. Okay. So we have this thing. And we didn't really spend any time looking at it. We just said, oh man, this is this ugly partial differential equation. I don't know what to do with it. Well, basically what this thing says is that the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y equals 0. So that these things are always equal and opposite. So if we look at this thing, and let's say we're looking at you guys can see my Excel, right?
Yeah.
Yeah.
So if we're looking at how things change in the y direction, what is the second derivative of temperature with respect to y doing that? What does it look like to you? Try to visualize that if you're just looking at, if you took this section and you were just looking at temperature versus y.
I don't know if it's a second derivative, but it reaches a minimum. It's like a parabolic with a minimum.
Yeah, it's an upward facing parabola.
Yeah.
Okay, what's it doing with respect to y to x?
The opposite?
The opposite, yeah.
Yeah, it's a downward facing parabola. So basically, this thing does exactly what we expect it to do. It's telling us that if you've got a highly positive second derivative here, a big upward facing parabola, then you've got a highly negative, a big downward facing parabola in the perpendicular direction.
Why is that the second derivative, not the first?
This is second derivative, yeah.
Okay.
Yeah. So it doesn't just work x and y. It applies to any two orthogonal directions. So if you, I know this thing looks like a rectangle because Excel is a little funny, but it's really a square. Make it look more like a square. Oh, too much of it. Yeah. So if we looked at this diagonal, this thing should apply no matter how you rotate your perspective, this orthogonality condition. So if we look from this corner to this corner, what's the second derivative doing?
Yeah.
Nothing. It's an isothermal, right?
Yeah.
Zero, right? So if we'll pretend this is our new like pseudo x direction. So if this guy is 0, what does this guy have to be?
Has to be zero.
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 So that we know that if this thing is, if this diagonal is going to be totally flat, this diagonal has to be totally flat. Same thing as if it's linear. So if it were just sloping up, we have any place where it just slopes, but not. I think from like here to here, it's roughly, very roughly, just like a no, it is. There is some curvature to it. Here, I think from here to, I don't know if I have an example of a place, but you can imagine that if you had a condition where it were the slope, where it wasn't totally flat, so the temperature would change, it was changing, but it was changing linearly. So it was just, 30, 35, 40, 45. Then that perpendicular direction would also, and
Just to get your pay, right?
what's that?
I think that was Maria's mom.
Oh. So this is the last thing that I set up for you guys, where basically instead of having top and bottom, I have the corners. So these corners are all 100, and then the other corners are all 0. And basically what you find is it's a little bit, because this is an even number of cells, it's 10 by 10, you don't get that perfect isotherm down the middle. But basically what you see is at the middle, it's pretty flat. And then as you go out to the sides, it changes. You get these cold spots and these hot spots. But the critical thing is any way that you look at this plot, you see that this diffusion equation is being satisfied. So here at this diagonal, we have that same slope that we saw here just across the x-axis. So it's highly negative parabola here, so then you've got a highly positive parabola here. From here to here, it's basically flat, not perfectly flat, but it's basically flat, so you're going to see something basically flat in the y direction as well. And you can really change this any way you want. I don't know if I have any, it's going to take forever to solve if I want to make a new one. But I'll send this out to you guys. And in particular, I think the solver works way better on Windows. So if you have a Windows PC, you can probably play with a lot more without risking doing damage to your computer. But that's really all I wanted to get out of today. I'm sorry that this discretization was a little bit sloppy. But the ultimate outcome is, and I'll just kind of restate this, that your heat rate all throughout the course depends on temperature distribution. In the past, we've used analytical methods to figure out the temperature distribution once we have an expression for heat rate. In two-dimensional, it becomes harder to do that. Occasionally, you'll find one-dimensional problems where it's hard to do that too. We've been dealing with very canonical problems. But occasionally, you'll have a problem where it's difficult to just go from your heat rate expression and immediately deduce your temperature distribution through ODE methods. So one option to solving that is these more complicated analytical solutions, like what we've been doing in class, where you use, I think the big assumption we used for this one was we assumed that your temperature distribution was a function, separately a product of a function of x and a separation of and a function of y. So the separation of variables. But a completely different approach is if we know that the heat rate has some dependence on the temperature distribution, and we have a numerical way of changing these numbers to force these guys to equal 0, or if we had internal heat generation, it could be equal to some non-zero term. Then you can also derive these expressions. And then the last point we talked about is the shapes of these topographies, you could say, look exactly as you would expect. They look exactly like what the diffusion equation says they have to look like. Any questions?
Go on, Joseph.
The numbers that we're looking at on the temperature distribution, are those the first derivative, or is it just?
These are the actual.
Yeah.
So I only labeled it here. But yeah, this is, I'm plugging in the boundary value temperatures, and then it's solving for the temperature. So you can imagine this is degrees Celsius. So this is solving for the actual temperatures in degrees Celsius in between. And basically what we've done is we've just set the heat rate to 0. If you could very easily make another one of these tables. Where you just look at, heat flux in one direction. So if you did this guy minus this guy, we don't have, you would want to have like a K term. But you could get your heat flux in the X direction this way. This is going to be some scalar. But I guess what this is saying is that heat is flowing down. So -50. It's not really watts. If K were 1, I think it'd be watts. But we ended up canceling out a lot of important stuff. But you could get your first derivative, which essentially is indicative of your heat rate from this. Is that your question?
Yeah.
Okay. I'll send out this spreadsheet. You guys can mess around with it. And then Cyrus, you had a question?
Yeah, so it was kind of Joseph asked it. It's like, so if we have like an internal generation, do we just, I guess for a numerical solution, we just put it in the heat rate, like for the solver, I guess, like put whatever the internal generation is?
Yeah, you can either go into the solver. The one thing that you guys should look at this YouTube video. They do it where they still include your K and your actual length scales. I canceled all of that out to make it as simple as possible. Mm-hmm. But if you kept track of them and you included them, then you could put in a heat rate in watts and make your solver fit that. So you can either have a constraint saying instead of equal to 0, something's equal to something non-zero, mm-hmm. Or you could just change this equation, +5. And then I don't know what the units are anymore, but you could basically just say that this whole energy balance is kind of has this offset. So it's, you know, there is 5 more being generated there than is being disseminated. I'm going to try this while we keep talking. If I'm going to set all these to 0. And then, oh, I'm just going to make it 1 everywhere. So it's 0 on the outside, and everywhere it's 1, and must be a formula. Not entirely sure how to do it. Anybody have more questions while I mess around with this?
Does the canceling of the K's also work for the analytical method that we do? Like, unless there's internal generation, like you said?
Does the canceling of the K's work for the analytical method? I think we do cancel the K's in the analytical method. Where did the K's go? Yeah, we basically did that kind of early, didn't we? Because we started with the diffusion equation. Right, of course. We start with the diffusion equation where you've already canceled out K and A.
Yeah,
So
but
okay.
But for like if we have internal generation again, then we have to bring it back, the K term.
If we have internal generation, yeah. Yeah.
So they're almost the exact same, the numerical and the analytical, except like the couple steps where we like mess around with the derivative, so we can just plug in temperature terms, right?
Yeah, I mean, the big difference is, so with the analytical, you get to here, and then you're doing this pretty funky PDE stuff to get at a solution, which is in terms of sines and hyperbolic sines. The numerical solution is we basically write out the energy balance that would give you this diffusion equation, and then we just use that directly. I'm gonna, before I send this out, I'll mess around and I'll try to create something with a heat generation term. But it diverges pretty quickly. I mean, it's the same. You're solving the same problem, but you're solving them in pretty different ways. So basically, you can't see it. Why is light today? Yeah, you start with your diagram, you go to your energy balance. What we did in class is we go out to diffusion equation, analytical solution, and there's all kinds of kind of ugly stuff here. It's important you know this stuff, but for me, it's a little more intuitive just to see what the solutions, I mean, it's kind of the equivalent of meditating with a problem. What solutions are we actually expecting? What is that diffusion equation, which at first glance just looks like an ugly PDE, tell us? And what it tells us is that you've got this relationship between the second derivatives when you are looking in perpendicular directions. Any other questions? How do we feel? Does this, I hope this helps more than it confuses you guys.
I think it's really cool once you actually see the things.
Yeah, I'm glad. There was a little bit of build up to that. I'm sorry that I got
Just a little bit, yeah.
in the middle. But I'll edit the sheet a little bit and send it out and make another tab that does internal heat generation. And what you're gonna see is there's gonna be like a hot spot in the middle, and then it's gonna cool off on the sides, which is exactly what you would expect. And you know, if you wanted to make this one-dimensional, you could probably, what would you have to do? You would change the boundary cell constraint to adiabatic. So you basically just say there's no heat transfer at that edge instead of saying that there is an energy balance. So it'd be a little tweak, but you could also model one-dimensional problems, and then you would end up with something very similar to what you've done before. I mean, I suppose the easiest way to do it is you just take a single slice, and then when you go in and do Q, your constraints are just going to be between the adjacent X cells rather than having energy balance in the Y too. I mean, that would be the easiest way. I might make another tab. I'll mess around with this and add some features to it before I send it out. So I'll do a one-dimensional version, and I'll do a 2D generation one, and you guys can play around with those. I think this will, having something visual to fall back on should be a little bit helpful, at least in wrapping your head around multidimensional. This is hard stuff. This is probably mathematically, the analytical solutions to this are mathematically the most challenging thing I expect to see in this class.